Questions about anything? Well, today's kind of a fun theorem. It will be a consequence of the argument principle called Rouché's theorem. And it has a very geometric interpretation that I'll tell you about now. It's about counting the number of zeros of an analytic function inside a simple closed curve. So I've got a simple closed curve gamma, and the inside I'll call omega. It's about comparing the zeros of two functions. When you use this thing, one of the functions you know how many zeros it has, and it's the other function you want to determine how many zeros it has. And here's the statement. You've got these two functions which are analytic inside and on that simple closed curve. And suppose on the curve, one of them is strictly less in modulus than the other. So on gamma. Then F is the one you usually know how many zeros it has, and F plus H have the same number of zeros inside gamma, counted with multiplicities. Which I should say, as always, counted with multiplicities. The thing to note right away is that inequality implies that neither one of these functions, f and f plus h, have zeros on gamma. So the thing to note, the hypothesis that h of z is strictly less than the modulus of f of z on gamma implies neither f nor f plus h have any zeros on gamma. So that implies that f and f plus h have no zeros on gamma. Let's see the y of that. Let's think about it for a second. Y. Well, let's see. That inequality, h of z less than mod f of z, that means that f is strictly not zero. It's bigger than h, whatever that is, and it's strictly bigger. So this is this shows that h can't vanish. F can't vanish because of that strict inequality. So why can't h vanish? Let's think. So f can't vanish, and I'll show you the picture of why that means that h can't vanish. So the important picture that gives you the geometric interpretation of this thing, we'll see h. We'll see that f plus h can't vanish either. Okay, so here's the picture. Is this is a picture proof. It's not going to be a proof. Picture proof. The proof is going to be the argument principle, but the picture proof is the way you remember this fact. So f of z is going to be me. F of z plus h of z is going to be my dog. Zero is going to be a telephone pole. And let's see, h of z is going to be the leash length. So let's think about this. Here's the telephone pole. And here's me, f of z, out here somewhere. And let's see, if I have f of z plus h of z, so this spot here is going to be f of z plus h of z. That's my dog. And so the leash length here, if you look at it, is the modulus of h of z. So the modulus of h of z is the leash length. And nowadays you have an extendable leash, so that can change. In the old days, that was a fixed length. So that's the leash length. And now if you think about it, what is the inequality? H of z less than f of z. Well, f of z, the modulus of f of z, is the distance from me to the pole. So this is the distance from me to the pole, and this is the leash length. And so it means I never let my dog run around the pole. And so remember, if the argument principle from last time, if you count the number of times f of z spins around the origin, that's the number of zeros inside of f. And what it means is that if I go around the pole 6 times and I keep my dog within the leash distance, less than the distance from me to the pole, the dog can't sneak around any extra times. So the dog would go around the pole the same number of times I do. So the argument principle we think we see, because we have intuition about walking a dog, we see that the dog goes around the pole the same number of times I do. And that is the number of zeros of f inside. Inside the path. And of course, so f of g would have the same number of zeros. So, what did I say? F plus h has the same number of zeros by the argument principle that I demonstrated last time. Okay, I'm going to demonstrate this in a minute. after I give an example. Questions about it? Kind of a cool thing. And it has other applications that are make certain things really easy. Like the open mapping theorem is, is going to be very easy because of this thing as a lemma. Let's see. So let me do an example here to show you how it's typically used. Let's have a z cubed plus 9z plus 27 on the disk of radius 2 about 0. How many zeros does this thing have? Well, you stare at that for a second and you realize, let's see, what's 2 cubed? That's only 8. I'm on the disk of radius 2. That's kind of dumb. Why did I think of this example? I thought I had a better one. Well, this is what I'm doing here is valid. If I had it on the disk, well, let's think. I see one that's obviously bigger than the others, namely this one. That's the big one. So that's going to be me. Actually, I'm not going around the pole. I'm just standing there, like, so it's kind of, and I'm keeping my dog. The other one's going to be the small one. So this is the big one. Typically, that would be F. That's equal to the F of Z. And the whole thing is going to be the F plus H. Okay, so which means that this part's going to be the H. And so if I want to use Rouché's theorem to see that this thing has no zeros, well, the constant one has no zeros. And so I got to show that this one has no zeros. And on the circle, we would have, let's see, on the circle, D2, the circle would be C2. Gamma equals the circle of radius 2 about 0. We'd have the modulus of h of z. That would be the modulus of z cubed plus 9z. That would be less than or equal to the modulus of z cubed plus 9 times the modulus of z. And of course, on a circle of radius 2, that's 2. So that would be 2 cubed plus 2 times 9. That's 18 plus 8. That's 26. Oh, that's kind of squeaking by. But that's definitely less than. So the aha here is that modulus of h of z is less than or equal to 26. And that's less than, strictly less than, importantly, 27, which is the modulus of my f of z. And so I have the hypothesis of Rouché's theorem, and therefore f and f plus h have the same number of zeros, which is namely 0. So f and f plus h have the same number of zeros. Inside. Namely 0. No zeros. Okay, so that's one way of doing it. Let's see, another example. You'll have some homework problems like this. Let's show all the zeros of z to the 6 minus 5z squared plus 10 fall in the annulus z such that 1 is less than the modulus of z is less than 2. First thing to note is that by the fundamental theorem of algebra, that thing has a total of 6 zeros in the complex plane. So I guess I should call that something. That's my p of z, a polynomial. So first thing to note, the fundamental theorem of algebra P has 6 zeros total, counted with multiplicity. So I want to show all 6 fall in that annulus. Okay, so let's think about the circle of radius 2 first. So on C2, let's think about which one is the big one. Then what, 2 to the 6 is pretty big, right? Is that 32 or something? So let's see, I would have z to the 6 minus 5z squared. That would only be 4 times 5, that's like 20. And 10 is only 10. So z to the 6 is the big one. That's the one I'm going to call f of z. And the whole thing, I want to show that f and f plus h has the same number of zeros as the big one. Okay, and so that means my h of z is going to be minus 5z squared plus 10. Okay, and so now I need to check my inequality. Let's see, h of z in modulus is the modulus of minus 5z squared plus 10. That would be less than or equal to 5 times 2 squared plus 10. That's 30. And 30 is strictly less than 32. 32, which that's the modulus of f of z, which should be 2 to the, that's the modulus of z to the 6. That would be 2 to the 6, which is 32. So sure enough, that shows that all 6 of the zeros, f has 6 zeros, inside. It has one zero of order 6. So it has 6 zeros in C2. So does f plus h, and that's my polynomial. Okay, so all 6 are in there. Now I have to see how many zeros there are inside the circle of radius 1. So next, on C1 of 0, let's see what's the big one. Then this z to the 6 would be only 1 in modulus. This one would be modulus 5. And this one's the big one. So this time, that's going to be the f of z, which has no zeros. And then this is going to be the h. And this one's going to, this is the f plus h, which is my p. And that one has no zeros. And so it's just like the first example I did. So P is going to have no zeros also. So it'll be the same as the previous one I did. And so what you see is that there's no CP has no zeros inside D1 0. And you remember the hypothesis implies there's no zeros on the circle either. So all the circles have to be strictly inside the annulus.
The f of z does not have to be inside of D, like the thing that you're looking for the zeros in.
The f of z?
Yeah.
No, that's a function.
Yeah, so it doesn't have to be within the domain. Like D1 at all. It doesn't matter how big f of z is, as long as h is inside of the domain, then it's fine.
Right.
Like, why is that?
Let's see, on C1. So you're thinking that my C1 has something to do with my let's see, me and my dog. The paths that I was drawing there was the path of me going around and the path of the dog going around, and those don't have anything to do with the original circle. So the original circle wouldn't be in my dog-me picture. That's the z of t is going around the circle, and the f of z of t is something completely independent of that circle. And so my f of z is going, it's like I had the picture of gamma in one here, and then the f of gamma in the other. The f of gamma is the circle I was talking about. Remember when I was doing argument principle? Jordan?
I believe 2 to the 6 is 64 above.
Probably that's even bigger, yeah, so that's even better. $64. Definitely less. Okay, so all the zeros, I guess to nail it, I should say, note. We know there's no zero. The hypothesis implies no zeros on those circles. On C1, 0, or C2, whatever I chose my f and my f plus h to be, either. So we conclude that all 6 zeros are in the annulus, the open annulus that I started with. Okay, that's a very typical application. Well, now I need to show you why why Rouché's is true. It's not hard. And it's a great thing because this is, we have this intuition about walking a dog, but that's not a mathematical proof. This is going to be a mathematical proof. So, some books use an F and a G instead of an F and an H. So let's see. I've got H is less than mod F on gamma. Let's let G equals F plus H. I want to show that F and G have the same number of zeros. Same number of zeros. Okay, so some books, let's see, so what I have the modulus of h is less than the modulus of f, h would be f minus g. All right. Yeah, f minus g. That would be h is less than f. Some books do this instead of the f and the h. They use an f and a g. Some books. But F and H is kind of nice because F is going to be the big one and the H is going to be the rest of the junk. So it's kind of easier, and I think that's why the book prefers this. And I used to prefer the F and the G, but it's changed my view. Some books use F and G instead of F and F plus H. But then it's harder to figure out which one's the big one. Well, it'd still be F, but it's hard to figure out what G is supposed to be. Okay, but we have that inequality. And so let's see. Remember, F is not vanishing on the curve, and so I can divide by F. Divide by the modulus of F. That would give me then I'd get F minus G divided by the way, F is never vanishing on the circle, so on the gamma, so I have F over F here. And I can put that inside, and I would get 1 minus G over F is less than 1 on gamma. I'll put that in a red box. That's kind of interesting. So let me draw my picture here. I've got a gamma curve. And I've got, I'll write capital F equals G over F. Capital F takes that green curve and multiplies and sends it to something that satisfies that inequality. All right, so what is that inequality? That means that f of z, capital F of z, is less than distance 1 from 1. Okay, so here's 1. And G over F is less than a distance 1 from 1. Okay, well, the set of things that are exactly a distance 1 from 1 is the circle of radius 1 about 1. Okay, so f of z takes that this is going to be f, capital F of gamma. It's inside that circle. And here's the origin right here. And so I'm thinking here, that's interesting. What this screams logarithm. And the argument principle has a lot to do with logarithms. So it's screaming to take the print. In fact, here's a nice principal branch of log. This is screaming that we ought to have a branch cut. There's the branch cut, and that's the principal branch. That's the principal branch. So it's the branch cut for log. Okay, and now here's the thing. These things are all nice up to the curve. So if I take a little open set like this around the curve, I'm assuming that f is analytic inside. These functions are analytic inside and on gamma. So there'd be a bigger open set where f is nice and continuous and differentiable, et cetera, et cetera. And so is G. And I could shrink that down by continuity to keep it inside this picture. So capital F would map in here like this. If I shrink it down enough, it would stay inside that blue circle. Okay, here's a fascinating thing. There's a famous thing called logarithmic differentiation. Capital F is equal to G over F. And you learned logarithmic differentiation, probably in freshman calculus. F prime over F is G prime over G minus F prime over F. You can just calculate that derivative and use the quotient product and say, yeah, sure enough, that's true. So that's easy to verify. It's just got that fancy word attached to it. So this is easy to check. You just write out the quotient rule and do it. But there's an interesting thing. I can make a log of f. That picture means I can write. There's a log of f is analytic. Capital F is analytic on the green curve. In fact, it's analytic in a neighborhood of the green curve. So the aha here is the principal branch of log of f of z is analytic in a neighborhood, a little open set containing gamma. Okay, so therefore, let's see, the integral around gamma of f prime over f dz, that would be the integral around gamma of the derivative of the log, d by dz, of the principal branch of log of f of z. dz, and by the fundamental theorem of calculus, that's 0. Because I have a function that's analytic in a neighborhood of that curve. Okay, and therefore that's equal to but the integral on gamma of f prime over f dz by that logarithmic differentiation fact. That's g prime over g dz minus the integral around gamma of f prime over f dz. I just showed you that's 0. Okay, and something's missing here. My 1 over 2 pi's are missing. I can just multiply everything by 1 over 2 pi I. Then, this one right here is the number of zeros of G by the argument principle inside gamma. And this is the number of zeros of F. And so, of course, they're equal. So that's the proof. It's just a fundamental theorem of calculus and this observation about logs. That's kind of all there is to it. So, of course, you have intuition about the dog and the walker, but I guess this doesn't give you much in the way of intuition in the proof, but it definitely works. Let's see. I guess I have time to do. I guess it's important that this is a closed curve to make this 0. If you integrate the derivative around a closed curve, you get 0 if it's analytic in a neighborhood. Well, one consequence of this that a major consequence that the book uses here, there's lots of different ways to do these proofs. So sometimes you pick one thing to be the starting point. But a major consequence for us is the open mapping theorem. Which is a surprisingly important fact about analytic functions. So the open mapping theorem says that analytic functions map open sets to open sets. Of course, they can't be constant because a constant function would map it to a point. So the open mapping theorem says non-constant analytic functions map open sets to open sets. That's simple. Let's think about why that's true. And why it has anything to do with So let's see. Let's suppose that f is not identically constant. So f is not constant. And let's suppose f of z naught is equal to w naught. Then f couldn't be constantly equal to w naught. So let's see. It's not constant. F of z naught's equal to w naught. So if I think about f of z minus w naught, it's not constant. It has an isolated 0. Otherwise, it would be constant if it wasn't isolated. I mean, if it wasn't isolated, then it would be constantly w naught. Okay, so here's the picture. Here's my z naught. Z naught gets mapped to w naught. I'm going to shrink down a disk about z naught, so it's the only 0 inside there. Okay. So I've shrink this down, shrink a disk. I might shrink it some more later, down, about z naught. So z naught is the only zero. Of f of z minus w naught in the closure. So even on the boundary. So that would mean that that blue circle would get mapped. Let's call this C. This would be f of C. Okay, I see now how I'm going to prove the open mapping theorem. I bet, here's the hunch, this I can now stick in a little disc like this. That little disc is going to get plastered by the map. And I'm going to use Rouché's theorem to show that. So I shrink down a disc like that in the picture, and I'm going to show that this, let's call that a disk of radius epsilon about W naught, gets hit by F. I didn't give this a delta. Let's call this a delta. I shrink it down. Gets hit by F in the disk of radius delta about Z naught. Okay, so let's see, why is that? Well, I'm going to pick a W in here. Say W is in that little disk in the picture. Rouché's is going to show me my f of z minus w naught and f of z minus w have the same number of zeros. Inside that circle. Of course, the w naught, the f of z minus w naught has one or more, and so that means the other one has one or more. F of z minus w naught has one or more. So the same for f of z minus w, w gets hit. And so that means that little open disk about w naught gets hit. And that means that my map is going to take open sets to open sets. Okay, that's the technical proof. So let's see what I want to show those two things have. So here's an annoying thing. I've got an F already. So I got to think. Let's think. How do you deal with, if you've already used your F and you need a different F, what do? You use a capital F. Let's take capital F. It's going to be the one we know. That's going to be f of z minus capital F of z is going to be f of z minus w naught. And then f plus h is going to be the other one. So f of z plus the h is going to be the other function, which is f of z minus w. And so that means the h, what's the h? I put that on the other side. The f's are going to cancel. So the what I need is h is going to be w naught minus w. That's a constant. And is that Okay, so I need, do I have h of z less than modulus f of z on the circle? Let's see, that would mean I would need w naught minus w less than f of z minus w naught on the circle. Go back and look at my picture. My w is in here, and that's this epsilon thing. And so w minus w naught is less than epsilon. And the distance from w naught to the z of t would be this distance. So this would be a z of t. This would be an f of z of t. And sure enough, epsilon is less than that from the picture. The way I chose everything. Yes. Epsilon is less than the distance from f of z to w naught. Check. Okay, so I demonstrated the open mapping theorem. The fact that that disk gets plastered about w naught gets hit means f maps open sets to f, since it was arbitrary. So it maps open sets to open sets because my z naught was arbitrary. Questions about that? It's kind of a theoretical moment, but it's not hard. And Rouché's theorem makes it particularly easy. I could have proved it using Cauchy integral formulas and sort of lots of epsilons and deltas and stuff. Wouldn't have been nearly as fun. Any last question?
So is the z, is that just from the circle of radius delta around z naught, or is that...
Right, that's the z of t. That's my curve gamma.
So the z is only from the circle and not any just arbitrary z within the open disk?
Right. So I could say on C. Check.
So why does that imply that the set, the image is open here?
I wanted to show that when I had this W naught, I wanted to show all the W inside that disk get hit. And so my two functions are f of z minus W naught and f of z minus W. They have the same number of zeros. That's what I want to show. And the f of z minus W naught has at least one zero. And they have the same number of zeros. That means the other one has at least one zero. And that means W gets hit. Yeah, it's kind of a mouthful. But if you sit around and look at that picture long enough, you'll believe me. And once you realize what you need there, then it's a matter of doing Rouché's and picking what the capital F and the capital H should be. And that's not too hard. This is one moment where the other version, the F and the G version, would be useful, because the capital F would be f of z minus W naught, and the capital G would be f of z minus W. And then you'd get it maybe more